Hello. Good evening to all. Now we'll start our programming session. In session, our expertise, Mr. Atif Khan. You are already know about him. So now in this session, he is going to uh, do hands-on clustering algorithms by using Python. Let's welcome to him to this FDP. I request Mr. Abdul Latif Khan to start his programming session.
Thank you, ma'am. Okay. Am I audible?
Yes, yes, you are audible.
Okay. Okay. So I'm sharing my screen. Okay. Is my screen visible?
Yes, yes, it's visible.
Okay. So in the last lab, I already shared one folder. So I renamed that folder as some ML, and I am again sharing its link so that you will get the access of resources and code for of both the sessions. So okay. So I have shared the link on the chat. So just access it, and okay. So in this shared folder, which is named as ML, uh, in this lab we will see this directory lab day 4, in which there are two folders. First one is real, which contains a real data set sum, and another is the synthetic, contains synthetic data sets, and this is Python notebook file. So in this lab session, we will see the demonstration of one of the most popular clustering algorithm, which is k-means, on some of the synthetic data sets and real data sets. So to run this code, as I already explained in the last lab, that just open this Python notebook, first connect it by clicking OK. So before it, you have to download it. So let me show it once again. So first you have to download this folder. So download this lab day 4 folder. To download it, click on this button, then click on this second last option. So a zip file will get downloaded to your local system. So this whole folder will get downloaded. Okay. So this is the downloaded file. First, extract this folder. So means unzip this folder. So we unzipped it. After unzipped it, here you can see this is the folder. So to run this code on Google Colab, you have to upload this folder which is downloaded. You have to upload this folder to your respective Google Drive account. So go to your Google Drive account. Suppose I wanted to upload it here in the collab notebooks folder. So I'm going to collab notebooks folder. Then to upload the folder, click on this new button. Then click on the folder upload. Then select the folder which we wanted to upload. So here in this case, we will work in this folder. So we are uploading this folder. So this whole folder is uploaded to my Google Drive account. It is currently uploading. In this folder, so now to run the code, just open this Python notebook file, which is named as k_means. Okay, then connect this Python notebook to the Google Collaboratory session platform. by clicking on connect, which was here. And after the proper connection, you can run this code, in which the code is divided by a cell. So run this cell, then run this cell, and by this uh, you can run the code. For the demonstration purpose, I am using this Colab notebook so that I can explain you better uh, how to code it. So first, first you have to connect it. So I'm connecting it. Okay, so I'm connecting. So it is connected. So first we have to import the required packages. So again, in this lab, we will again work on the numpy arrays. So I am importing numpy package, giving its alias name as np. Then I am importing pandas package. Again, we will work on the CSV file. Our dataset will be in the form of CSV file. So I'm importing pandas package and aliasing it as PD. And for which in this lab session, we will also see demonstration of k-means clustering on synthetic data sets. So which is a two-dimensional data sets. So synthetic data sets are useful for the visualization purpose. So to visualize the data set and see the how k-means work visually. So for visualization purpose, I am importing and we will use matplotlib library, Python's matplotlib library. So from matplotlib, plotly, there is one sub package named as plt. So I'm import pyplot. There is some sub package named as pyplot. So I'm importing this pyplot package and aliasing it as plt. Okay. So our required packages get imported. In the next step, we will we will see we will work on the synthetic data sets. So let's see how synthetic data sets looks like. So first, to load the synthetic data set, again, since our data sets are on the Google Drive, so we have to first mount our drive. So to mount it, click on this folder icon, and then click on this mounting drive. So here in this case, this you have to mount it, this code will appear. So you have to run this code. So just run this code, give some credentials, access gives access. So after the successful running, the drive should get mounted. Okay, so our drive get mounted. So now we can perform read write operation on our Google Drive. So from to or from our Google Drive. So here you can see that this is our drive folder. This is my drive folder. Inside my drive, I have uploaded the folder which is the lab default in the Google Colab notebooks folder. So inside Colab notebooks folder, there is this our directory lab default. Since we will work first on synthetic data sets, so here you can see that all these are the synthetic data sets. Some synthetic data sets. So synthetic data sets are nothing but data sets which are created synthetically just for the demonstration purpose or just to analyze visually that how a particular clustering algorithm works, what type of data sets or on what type of clusters it can detect the clusters, or what type of distributions on data set the particular clustering algorithm will work. So just to analyze visually, we were on the synthetic data set, and it is a two-dimensional data set. So let's suppose there is one aggregation data set. So just open this file. So here you can see that this is the header. So each row representing a data point. So this is the first data point, this is the second data point, this is the third data point, and so on. So wait. Okay. So, and column, first two columns represent the value of the data points along a feature. So First column represents the value of each data points along first dimension or first feature. Second column represents the value of the data points along second dimension or second feature. And the last column represents the ground truth labels, means to which cluster it belongs. It means that the first cluster, the first data point belongs to cluster 2, in which its value along first dimension is 15.55 and its value along second dimension is 28.65. So this is the data set. So first we have to load this synthetic data set. To load it, we will use pandas library. So from panda, all function read csv. Inside it, first we have to pass the path of the file. So let's see. So to get the path, go to the file by this navigation, directory navigation, and select the select copy the path of the file. To copy the path, click on this three dot and then the second last option, copy path. Then copy the path. Also, in the last lab, the data sets which we saw, the separator of for those data sets were comma. So for that, we don't have to pass the separator parameter because the default separator parameter is comma. But in this aggregation data set, we can see that the separator means the data points are separated by some other character. It is not comma. So here we can clearly see that the each data entries or data entries of each row are separated by tab slash t. So here in this case, so if we run it, then the data set will not get loaded properly. Here you can see that it is showing only one column, but in our data set, actually there are three columns. So why? Because the separator value of the separator parameter is incorrect. So to do that, we have to pass another parameter which is separator, which is sep equals to s slash t. Okay, so now the data set, our data set got loaded. So I am storing it into the variable df. So df contains our data set. And also, since this is the pandas, we are loading using the pandas library. So this data set in the form of data frame. So if we wanted to just print starting rows, so just use df.head, since we wanted to print only starting 15 rows. So df.head and pass as 50. Also, another thing is that in for some cases, data set will not contain this header part. In this case, suppose let's open this aggregation data set once again. In this data set, we can clearly see that this there is one header field which tells about the information about the column. This x means the value along first dimension, y means value along second dimension, and cluster labels. But some data sets there is no columns. The first starting row will starts with the data information related to the data points. For example, this G12 data set, so here you can see that this G12 dataset doesn't contains any header field. It only contains the value of the data points along the features. So in this case, so let's say I am opening this dataset, G12 dataset underscore k equals to 3. So here you can see that the useful information, which is the first data point, will be the part of header, not will be the part of a data. So to not avoid the header, we have to pass another parameter. In this case, for G12 dataset, which is the third parameter, header. This is the parameterized argument, header as none. Okay. So our G12 dataset here, you can see that get loaded, and since there is no header, so it assign headers in the or index of the columns starting with 0. Okay. So on this data frame, we can perform many operations. The most simple operation is accessing the elements using the index. So suppose if I am accessing 0th index, so it will return values of the data point along zeroth column. If I am passing one, value of the data points along first column. So by default, I mean, in most cases, if we work on the numpy arrays or normal arrays, then if we simply write index, then it will first select the row. But in this case, it is selecting first column. If we wanted to first select row then column, then we can use iloc .iloc. So using iloc we can access the elements of the data frame using indexes, in which the first part will be the index value of the row and second part will be the column. So suppose I wanted to select this point, it means that value at second row and zeroth column. So we can type it as 2 comma 0. Okay. We can also perform slicing on it. For example, if we wanted to get information of first 5 data points along first dimension, means we want this value, this value, this value, this value, and this value. First 5 rows or first 5 data points along second dimension. So to do that, we can, since we want starting 5 data points, then we can also perform in slicing also. So by this we get start data points of starting 5 rows or values of starting 5 rows, and since we want first column, so passing it as 1. Also, negative indexing is also there. So suppose if we wanted last column values along last column, so we can type 2, because here in this case index at index 2, which is the last column, or we can also type it as -1. So since negative indexing is applicable in Python's standard data structures, and it is also applicable in data frames also. So with the help of iloc, in this case we will separate our data part and column part. So to get the data part, since we want all rows, so in the row column we are typing it as just colon. So it will get all the rows, and since the data part should not contain the last column, so we are accessing the columns or element values by avoiding the last column. Here by this we got the data part. Since this is the data frame, so in the further part of the code we will work on the numpy arrays, because I am more comfortable and habitual about working on the numpy arrays or arrays. So to convert this data frame into the numpy array, we can pass this data frame into np.array. So now this data frame is converted into arrays. uh, to get the label part or the cluster labels, we can again perform indexing on it using iloc. Since we want all rows, so again we are passing as colon, and we want this time only last column, so we are just passing -1. No need to perform slicing as here. We just need the details of one column, and again converting this into numpy arrays. Okay, so it is converted. So now I am storing these data part and labels part into variables. So in data part will be to X variable, and label part will be assigned to actual labels. If we wanted to know that how many number of data points and features are there in our data set, so since our X numpy array contains the number of rows will be same as the number of data points, and number of columns or number of features in the X data set will be the same as the number of features. So to get the number of columns, number of data points and number of features, we can use X shape property. So using X dot shape, it will return number of data points and number of features. So our data set contains total 300 number of data points, or this G12 data set contains total 300 number of data points, and having, since this is synthetic two-dimensional data set, so obviously it is having total 2 number of features. So storing it into variable N, and F to get the number of clusters. Now, since we will see the demonstration of k-means. So for k-means, we required input parameter k. K means the actual number of clusters present in the data. So to get the actual number of clusters, so here you can see that this actual labels variable contains the cluster labels. To get to know that how many total different cluster labels present in our data, we can convert this array to the set. So the set, by converting it, it will only contain the unique values. So it will only contain the total unique cluster labels are present. So there are total 3 cluster labels are present in our data. The first cluster is having the label S1, second cluster is having label S2, means all the data points that belongs to second cluster will have the label 2, and all data points which belong to the third cluster is having the label 5. To get the number of clusters, we can pass this set into the length function, which is len, and we get the number of clusters. Okay, so in our data set, the number of data points are n, number of features are f, and number of clusters is k. Okay, so is there any doubt till now?
Sir, how to define how many number of clusters would be there?
Okay, okay, it's a very good question. So, currently, the data set in which we are working, the data set contains the this label part. So, on the basis of at that we can get, but in the cases in which you can get the data set where in which there is no information about the number of clusters, then in that case, the finding the number of clusters is then for that you have to also detect the number of clusters in that data set, which is itself one of the challenges of clustering. So if you don't have number of clusters, so then and you wanted to perform k-means, then there are some statistical methods like performing elbow method, or the better thing is to go to the other method like density based clustering, in which the it is not required number of clusters as a parameter.
By elbow method, we would come to know that what would be the best value of k that we would take
Yeah,
for our
yes, yes,
clustering technique.
yes, yes. It is, but for sometimes it is helpful. But
Okay,
yeah,
okay, okay.
okay. So after this, we will visualize our synthetic data set. So to visualize our synthetic data set, we will use using the matplotlib library. So we will see the scatter plot. So first thing is that in our x variable, it contains the data set. So to get the value of the data points along first feature, so we can get it by again using the indexing. So the first we want all rows, means information of all the data points, and value along the first feature, means at the zeroth index, means all row and zeroth column. So this is the value of the data point along first feature. Value of the data points along second feature will be all rows, then only first column at first index. So by this we get this. To plot it from PLT, call scatter method, in which the first parameter will be the value of the data point along x dimension, which we already mentioned. Value of the second parameter is value of the data points along y dimension, which we already mentioned, and then just run it. So here you will see the visualization of our data set. So this is the visualization of G12 data set which we loaded. and in which we can see that this data set contains total three number of clusters, in the clusters, and those clusters are nothing just the three blobs. So this is the centroid based clusters, and we can apply k-means on this, and k-means is able suitable to detect clusters for such kind of clusters data sets. Also, in matplotlib library you can also use various other things, like you can change the size of each marker, like
Sir, by visualization, we can also know the number of data points in each cluster.
we can know, but it will be, I think, a hectic task. If you mean by number of clusters, then yes, we can see by visualization. So yeah, if finding number of data points, then it will be a hectic task. You have to count each data point.
No, is there any technique for finding the number of data points which is residing in each cluster with the help of this matplotlib or something?
I think I have no idea much about that. But
Okay, okay. But
if you
just
want,
some
yeah, yeah,
general interpretations we can have, like
yes, correct,
maximum number of data points lie in which particular cluster or something. We can have that
correct, correct. We
general
can
type
have,
of
yes,
interpretation.
yes, correct.
Okay.
I mean, by visualization, we can intuit that which data point is which cluster is having which data point, and we can
Sir, in the previous up in code, you have used that set function. What is the purpose of that? Actual labels. Okay, and this np.unique is also doing the same thing, no?
Yeah, np.unique also doing the same thing, but I am demonstrating this to get to know that how many number of data points are belonging to each cluster. So for cluster label 1, there are total 100 number of data points. For cluster number 2, there are also 100 number of data points. For cluster 5 also there are 100 number of data points. So by that, to get the number of data points cluster wise, you can use np.unique.
Okay, okay.
Okay, so let's see again this matplotlib scatter plot. So you can change the marker sizes also, means the size of each marker, and you can
Change the
also,
color. uh,
yes, you can change color also by suppose
It will
giving color.
assign each different color to different clusters. Then it will show
Yeah,
the.
yeah, yeah. Correct, correct. I will demonstrate that part also.
Okay.
Yeah, yeah. So let's give size as suppose 30, and you can also change the marker type. Suppose let's see we want marker as square. So just marker equals to s. So each date, scatter plot of each plot is having a square marker. We can also change the dimensions of this plot also by giving as plt dot figure and giving fixed size means length and width in the form of inches. Suppose let's say length will be 10 means wide and height will be 7. Here you can also change this, and you can also in practice it is better to use plt.show, and then you can also give the title also. Title, I think it is very large, we can reduce it 7 by 5 and let title as that input data set. This is our input data set. So what's our aim? Our aim to detect these three clusters using k-means. So let's see how to, okay, so to visualize it, cluster wise means one cluster, data points of one cluster should have different cluster, and data points of data belongs to another cluster should have different color. So to give the color cluster wise, first let's see how to change the color. So there is one parameter C in which just pass as suppose red. So color of all data points will be red. To get the data to assign the colors to each data points uh, based on the labels, actual labels or clusters. So here we can use these actual labels and just pass this actual label as, as a C parameter. So on the basis of the labels of each data point, the color will be mapped. Okay, so this is the our data set with the ground truth labels. Means there is one cluster that belongs to this. That so all these data points which are in yellow color belongs to one cluster. All data points of this purple color belongs to another cluster, and all data points of this blue color belongs to another cluster. So just provide its title as say cluster input data set with actual labels. Okay. So in the next phase, we will apply k-means on this G12 data set. So to apply k-means, the first part we will see using the inbuilt function. So again, sklearn is very popular library which provides so many inbuilt functions related to the machine learning algorithms. So in sklearn, there is one package named as cluster. This cluster package contains so many popular clustering algorithms and standard clustering algorithms, and we can use those functions of those algorithms. So inside this cluster, there is one class named as k-means. Okay, so this is a class. So we will use this k-means class to perform k-means on the G12 dataset. So to know the definition of this k-means class, we can use this help function. So here in this definition, so we can see that this is a class in which to create the object of this class inside in its constructor, we have to pass one must parameter, which is the number of clusters. So just call this constructor of k-means class. First parameter will be number of clusters. As I already, okay, it should be cluster.k-means. The number the variable k already contains the number of clusters. In it, what type of centroid initialization you want? Default is k-means plus plus. Since this is the first demonstration, so we will see just random initialization, random centroid initialization. To do that, pass random as a init, and next is number of init. How many times you wanted to perform k-means? So let's say we wanted to perform k-means for a particular data set for 3 number of times. So k-means will perform for 3 times, and among it the best result will get. So just run it. I am storing the object into the reference variable km. Now to run the k-means on our data set, so just from km call the function fit. Since we are clustering is an unsupervised learning task, so we will only use data. We will not use the actual labels. So we have to just pass x, and k-means will learn on this data set x, and centroids will get learned. Okay. To get the labels, what are the labels predicted by the k-means, or what are the cluster labels predicted by the k-means on this G12 data set? So we can get those labels by from km call a attribute named as labels underscore. Okay, so this from this km dot underscore labels, we can see that what are the labels assigned, or what are the cluster labels assigned by the k-means to the data set. So according to this, the first data point belongs to cluster 0, second data point belongs to cluster 0, last data point belongs to cluster 2, and for all the data points, you can see their cluster labels. So I am assigning these labels into a variable, let's say predicted labels, labels predicted by our k-means. Okay, now we can, since this is the synthetic data set, so we can also visualize this result also. The clusters detected by our k-means algorithm, we can also visualize it. To visualize it, again, we can reuse this code, and here clustering result. And here we can we should pass this predicted label. So these are the cluster labels predicted by our k-means algorithm. So here you can see the results of the k-means. So here you can see that k-means detect the clusters very well, and in fact perfectly for this data set. And all the data points that are having yellow colors belong to one cluster. All the data points that are having this green color belongs to another cluster, and all these data points belongs to the third cluster. So when we are working on synthetic data set, so for that we can just visualize it, and just to check that whether we are getting the desired clusters or not. Okay, in the next part we will see user defined function which I made. And the purpose of this activities is to see that how k-means work step by step. I mean, how k-means learning these centroids and getting these desired clusters. So to do that, we implemented this uh, algorithm k-means step by step. So these are the steps of the algorithm of k-means. So the first step is to simply initialize the k centroids and run the k-means for maximum number of iterations, or until we get the consecutive centroids. So, and the each iteration is having two steps. The first step is to first form the clusters by assigning the closest centroid to each data point, and second is to again find the centroids of the newly formed clusters. So these are the two steps of each iteration, and because of these two steps we are getting better and better clusters in each iteration in k-means. So let's first we should run this code. So to run this code, we can see the definition of this my k-means function, which is the user defined function. So just call this my k-means function. The first parameter will be the data set, in which we have to detect the clusters. Second is the number of clusters. Currently, there is no need of this. Let's say k-means will run for maximum 20 number of iterations. And to see that the results of k-means in each iteration, we are passing is plot as true. Okay, and just run it. I think, let me run this once again so that for the better explanation. Okay, this is better example. So the first step is to in this case we are using random centroid initialization. So firstly, in this case number of clusters are 3. So three random centroids have been initialized. This is the first centroid, this is the second centroid, and this is the third centroid. For iteration 0, again we then for each iteration we will perform these two steps. So the for iteration 0, the first step is to um, assign assign closest centroid to each data point. What it means that, suppose for this data point the closest centroid is this, and here initially the centroid is represented as the red marker. For this centroid, for this data point the closest centroid is this. For this data point closest centroid is this. So it means that all these green data points are having closest centroid this. All these purple data points are having closest centroid this, and all these yellow data points are having closest centroid this red marker. By this we got three clusters. So this is the first step. The second step is to again recalculate the centroids of these new clusters. So the centroid of this green colored cluster is this, centroid of this blue colored cluster is this, or centroid of this yellow colored cluster is this. So this is the second step. Now for the iteration 1, these blue colored markers or these new centroids will be the centroids at the beginning of iteration 1. So here in these blue color markers change to this red color marker. Red color markers means centroid at the beginning of iteration. Blue color markers means centroid at the end of iteration. So now these are the new centroids. I mean, or the centroids at the beginning of iteration 1. Again perform the same two steps. So all these green data points are the data points that are closest to this red colored marker or this centroid. All these purple colored data points are closest to this marker, and all these yellow colored data points are closest to this marker. Then again recalculate the centroid. So these blue colors are the new centroids, means the centroid of this green colored cluster is this, centroid of this purple colored cluster is this, and centroid of this yellow color cluster is this blue data point. Again, now this blue data point will be the centroids at the beginning for iteration 2. Then again perform the same two steps, assigning the closest centroid to each data point to form the cluster. And then the second step is to recalculate the centroid of the newly formed clusters. So here you can see that in each iteration we get better and better clusters, and the centroids are shifting to the optimal or global solution, optimal minima or global minima. So the centroids are shifted such that the data points, the clusters are formed around those centroids, and which we are getting the better and better clusters, and at the end desired clusters. Also, here you can see that there is one value which is the SSE. So the aim of the k-means is to minimize the SSE. SSE means sum of squared error. So for iteration 0, SSE is 12.55. In iteration 1, we got better clusters compared with iteration 0. So SSE also SSE is lower in iteration 1, which we can see as compared to iteration 0. For iteration 2, SSE is further lower as compared to iteration 1, and so on. And again, finally, in the iteration 3, we can see that the centroids is not shifting more, means that for consecutive iteration we got the same centroids, so we can stop our k-means and we can terminate it, and these are our final clusters. So this is the working of k-means. uh, to calculate the SSE, I have implemented this cal underscore SSE function, in which SSE means sum of squared error, means finding the sum of square of distance between each data point to its centroid. What it means that if we wanted to find the SSE for this cluster, for this or let's say SSE for this scenario, so find the distance, square of distance between data points, so it means this, and to its centroid. So distance between this and this centroid, distance between this data point and the centroid, distance between this data point centroid. Take square of distance and take sum. So by this we got this SSE. SSE should be minimum. And the aim of the k-means is to minimize the SSE. So here we are doing nothing, just to calculate the SSE first for each cluster, adding it and return the final SSE. So first SSE variable is initialized as 0. This underscore I will return the index, means in centroid of centroid of first data point, which is at zeroth index, and centroid of second data point, which is first index, and so on. So what we are doing, that let's say set, let's say suppose this is clusters, you know. So set of cluster, let's say what is cluster is doing. Clusters variable contains all the cluster labels. So set of clusters will return all the different cluster labels present in the labels variable. So this is, suppose, let's say this will be label 0, this will be label 1, this will be label 2. So for each cluster, we are running this code, and we are calculating square of Euclidean distance between the data points of that cluster and the centroid. To get the centroid, we can use this centroids variable. So let's say what is the centroid of first cluster, which is formed finally. So centroids of 0 will return the centroid of first cluster. And to get all the data points, let's say that belonging to cluster label 0. So for that, we are using this np.where function. What it is doing, so if we wanted the index of all those data points that belongs to cluster 0, so for that we can use this np.where, and we can apply that query. So first call function np.where, then all those data points that belongs to cluster 0, means we are passing it this condition. So this will return index of all those data points that belong to cluster 0. And to get the data points, just since our X data set contains the data points, these are the data points. So we want the values of those data points at these indexes. So since we are using numpy, so it will uh, allow multiple indexing. So just pass X and this index. So these are all those data points that belong to cluster 0. So uh, So by this, we are iterating to each cluster label, then getting the data points that belongs to that cluster by this, getting the centroid of that cluster by this, and just calculating the square of Euclidean distance and getting the sum. Uh, this is the inbuilt function. This is the user defined function my k-means, which implemented these three steps. If there will be the time at the end of this lab session, then I will explain this line by line. Otherwise, there is this is commented well. So, and if you have any doubt in this code, then you can ask me. Okay. So here we saw that step by step visualization of the k-means and how k-means works. So okay, so this is the thing which we already did. Now, so just to simply call, how to call this my k-means function simply and without any this step by step visualization. So to do that, call this function and just pass its plot as false. Okay, so our clusters variable, this function returning three things. The first is the cluster labels predicted by the k-means. Second is the initial centroid which have been selected at the start of k-means. And the third is the final centroids, which is the learned centroids which we get after completion of the k-means. So uh, this clusters contains the variable. Okay, so again to visualize it, we can use plt.scatter. So plt.scatter, then passing the values of data point along first feature, passing the value of data points along second feature, assigning the colors based on the predicted cluster labels, which is belongs to clusters, and then just plt.show. Okay, so here these are the clusters predicted by the user defined k-means. We can give the title clustering results. And what else? Okay, we can also visualize these initial centroids. What are the centroids initialized uh, at the beginning of k-means? So we can also visualize that. So again, to visualize init centroids, again call plt dot scatter uh, value of the centroids along first dimension, value of the centroids along second dimension, and let's say marker, give marker as star and color as red. Okay, the marker size is so less, so we can give it as s equals to, let's say, 200. Okay, then also we can print this final centroids. Marker as this. Okay, so these are the clusters predicted by the our user defined k-means function on the G12 dataset. And here you can see that it is detected well these three clusters. These red markers are the initial centroids, which is selected randomly by the k-means, and these blue marker are the final centroids, which is at the completion of the k-means, after the completion of k-means. Okay, so, since we can see that the first step is to randomly initialize the centroids. So, because of that, the results of k means is depending upon the centroids initialization, and due to this, the results of k means varies in each run. So, it is a non-deterministic clustering algorithm whose results varies and depending upon the centroids initialization. So here, the in suitably selecting the initial centroid is the crucial part of k-means, and if uh, centroids have not been initialized properly, then it may uh, unable to detect the clusters or may take more iterations to reach to the final results. So this is an one example in which we have passed, in which there is one example in which there is a good centroid initialization and we got the final clusters, and there is an example, second example, in which there is an example in which the centroid have not been initialized properly or not properly in terms of getting the appropriate clusters. So here you to give the initialization manually, this user defined function also provide that facility also. So here you have to just pass this init centroid and pass the centroids manually. So here for this case, the first centroid will be 0.2 comma 0.6. Coordinates of the first centroid is 0.2 comma 0.6, so which is this. So this is the centroid, of first centroid, coordinates of first centroid. Then this is the coordinates of second centroid, and this is the coordinates of the third centroid. And in this case, you can see that the initial centroids are well scattered, means they are far apart, and and when k-means will get learned, we get the final clusters properly, and also it will take less runs to get the final clusters. This is the another example in which these two clusters are very close apart. These two centroids are very close apart, and this is the third initial centroid. And for this initial centroid, here we can see that we didn't get the desired clusters, means k means didn't reach to the uh, global optima, and we didn't get, and we get the poor clusters. Why? Because as I already told that for bad centroid initialization, k mean may reach to the improper clusters. So if you wanted to check more, you can load more these synthetic data sets, and also you can give the centers manually to check that for what kind of centroids we will get the desired clusters and for what we will not get. Okay. So because of that, it is advised that when we are performing clustering using k-means, run k-means for multiple runs and consider the average result or best result. So this is the code in which k-mean is running for 10 times, and each time k-mean will get run, we get the result, calculating the SSE, and for the case which we get the minimum SSE, we are storing those cluster labels and considering that cluster label as the final label. So okay, so here you can see its result. This is the k-means result with least SSE among 10 runs. So it is always advised to run k-means for multiple runs and considering the best result or average result. Okay. Is there any doubt till now? Okay.
No, sir, it's clear.
Okay, okay.
Yes, sir.
Okay, so in the next phase, we will see. So synthetic data set are just for the if you are designing any clustering algorithm or you wanted to visualize that how on what kind of data sets that clustering algorithm will work, then synthetic data sets are good. But when it comes to the real world application, we have to deal with the m- more than two-dimensional data set or multi-dimensional data set. So here in this next phase, we will see the performing clustering on some real data sets or how to perform k-means clustering on real data set. So in the real folder, there are some real data sets are there. So let's say this iris data set, which I already explained. So in this iris data set, separator is comma, and in this data set, it contains the information of the iris plant of 3 iris species. So here in this case, if we treat this data set in terms of clustering, then we have to detect 3 number of clusters. So to do that, first we have to load it. So we have first give the path of the iris, this data set path. Second parameter is the separator, in this case is comma. Is it comma? Let me see once again. Okay, it is comma. And this data set in this case not contains any header field, so header has none. Okay, let me give the path. Okay, so this is a data set, and again we are separating the data part and the actual labels part using the df.ilog and converting both those two things into the numpy arrays and getting the number of data points, number of features, and number of clusters. So the iris dataset contains total 150 number of data instances with 4 number of features and 3 number of clusters. So we are using this inbuilt library, sklearn k-means, in which the first parameter will be the number of clusters, which is with this variable k. The second parameter will be the uh, initialization. In this case, we are using the random initialization, so passing the random, and number of init as 10. So for this case, the k-means will run for 10 times on the iris dataset, and among 10 runs, the result with best minimum SSE will get returned. To run k-means on the dataset, call fit function from km and pass the dataset, which is x. To get the cluster labels, we can use this labels underscore property. This will return the cluster labels or cluster labels that has been assigned by the k-means to each data point and stored to the print labels variable. So since this is the real data set, so there is no direct way of visualizing it because in this case it is the 4 dimension. So but we can see that cluster labels. So our first data point is predicted as it belongs to cluster 1. Second data point is belongs to cluster 2 according to the k-means which we have called. Third data points belongs to cluster 3. Fourth data point belongs to again cluster 1, and so on. So we can see this. Okay, so since we can't visualize the cluster or data points, so but still we have to analyze the performance of the k-means algorithm, that how k-means algorithm performs on this iris data set, and to perform some quality measures whether it performs good clustering or bad. So to do the cluster analysis uh, on the real data set, or in generally we can also do this analysis on a synthetic data set. There are generally two measures. One is the internal measure, second is the second type is external measures. So internal measures are those performance measures which do not considers the actual cluster labels. Means that while performing or by the clustering quality of a particular clustering algorithm, we will not use the actual cluster labels. We have already saw one popular internal measure, which is the SSE. If SSE is less, it means that it is good cluster. If SSE is more, it means that it is relatively bad clusters. So to get the SSE, we can use this call SSE function, which we have already implemented. Okay. So to get the SSE of the clusters or the predicted clusters, uh, call this function call SSE. First parameter is the data set. Second parameter is the cluster labels. In our case, the cluster labels belong to print labels. And the third case is the centroids, which is final centroids which have been learned by the k-means. So since we are using this inbuilt function to get the cluster centers, final cluster centers, let me use this help function to get the property by which we will get the final cluster centers. Okay. Okay, so you can see that there is one attribute belongs to this class, which is cluster centers. So from the object of this attribute, from the object of k means we can call this attribute. So by calling km dot cluster centers. Okay, so these are the cluster centers or centroids of each clusters which have been detected. So this is the cluster center of first cluster. This is the center of second cluster. This is the center of third cluster. So we have to pass this as a third parameter to get the SSE, because SSE considers the distance between the data point and its and their centroids. Okay. So by this we got the SSE. So by this we got some numerical value. So for this case, the SSE is, it will 78.94 something. Okay. The another example is external. Another type of performance measures are external measures, which will consider the actual cluster labels as well. Okay. So in this case, we will see two types. One is the RAND index score, and another is the clustering accuracy. So clustering accuracy uses the confusion matrix similar as the class accuracy related to the classification. So the confusion matrix will be made between the between the clusters which have been predicted and the actual cluster labels. So let's say in this case, the both number of clusters and number of classes means the actual labels will be 3. So the confusion matrix will made of 3 cross 3. But okay, first let me see how to get these values, then I will explain later. So to get the rand index score, call this rand function, which is belongs to the sklearn.matrix package. call this rand score. Since this is the external measure, so it is required to pass both two things, which is the predicted labels and the actual labels. The predicted labels is belongs to this variable pred labels. Actual labels belongs to this actual labels. And by this we got rand score. So this is the rand score, which is something 0.8797. So this is, it is also named known as a rand index. So rand index is this. To get the clustering accuracy, call this clustering accuracy function which we have made. Again, it is required same two parameters, which is the predicted labels, cluster labels, and the actual cluster labels. Okay, so I'm storing it into the CA and just printing it. Clustering accuracy is, we can also round it. Suppose we wanted to round it up to 4 significant digits. So both the values of Ri and clustering accuracy varies from 0 to 1. 1 means the perfect clustering, 0 means the poor clustering, means better the values of Ri or Ca, means better the clustering results. Okay, so now we were talking about how clustering accuracy differs from the uh, classification accuracy. So first, the clustering accuracy uses the same confusion matrix, which is between the actual labels and the predicted labels. Then, but the main difference is that we have to map which cluster labels belongs to the which cluster label. We have to map between the predicted cluster label and actual cluster label. What it means that, suppose we have this actual labels. Okay, first let me give the example of for synthetic data set. It will be clear better. So what is the challenge? One of the challenge in while calculating the performing the external measures in clustering. Okay, so here you can see that suppose in this G12 data set, these are the labels of actual data sets, and these are the labels of predicted labels are predicted by the k-means. So here you can see that when we are running it, we can see that our k-means algorithm detected well the clusters, but the cluster labels are different. What it means that the first cluster in the actual labels are belongs to label 1, but in this case in case of predicted labels, the first clusters are all the data points of are belongs to the first cluster, but their cluster label is different, which is 2. So here it is 1, here it is 2. Here in the second cluster label, for second cluster the actual label is 2, and for in case of predicted labels for second cluster the label is 1, and also it is differ for the third case. So when we will calculate the measure or finding the performance measure, we have to map which actual label is mapped to the predicted label. So for doing that, we have to so let me print this classification clustering accuracy. So you can see that this is the confusion matrix, but we have to use another thing, that since we have to also map the actual labels and predicted labels, so we have to reshuffle the columns such that the sum of diagonal will be maximized. Why sum of diagonals should be maximized? Because the formula of accuracy is that sum of diagonal divided by total number of data points. So after this, after getting the confusion matrix, we have to also perform this linear assignment operation, which is nothing but shuffling these labels such that our diagonal should be maximum. Let me print this again confusion matrix. So these are the original confusion matrix, and the second we are printing the shuffled confusion matrix, which means after the mapping. Okay, so here you can see that this is the original confusion matrix, and after shuffling it such that we have to maximize this diagonal, we get this confusion matrix, and then just simply applying the accuracy on this confusion matrix to get the final results. So by this clustering accuracy differs from the classification accuracy, and okay, so that's it. Is there any doubt? Okay, I think there is should not be any doubt. So this is from my side. If you have any some doubt or wanted to explain this code, I can, or otherwise we can speak it. So
I think on other external measures can be also calculated by using this Python code, jacket, adjusted rand index.
yes,
Those
yes, we
are also
can.
calculated by this. I
Yes, we
think
can calculate. Yes, other measures also we can calculate. So there is one library which
yeah.
is so from sklearn dot matrix. There is one. Okay, so there is one function to calculate the adjusted rand index.
Okay.
All this adjusted rand score, and okay, then just call this function. So it will get the ARI, and
Yeah. Right.
yes, ARI, which is adjusted rand index. And since this is the external measure, so again we have to pass the predicted labels and as well as actual
The actual
labels.
levels.
Yeah. So this is the ARI. Actually, this is the ARI for this synthetic data set, which because we have loaded it once again, we can run it once again. Okay, so for iris dataset, K means performed clustering with ARI of 0.73. Also, there are also other measures like okay, there you can use this. There is one. Okay, if you wanted to know all possible
All
measures
possible
available,
external measures where we can find it.
yes, yes, we can find it. So again, this is a very good function, help function. Either we can go to the official documentation or see it of this sklearn, or we can see it here, just passing this package to the help function. Sklearn. Okay, okay. So this is the complete documentation. So let me scroll it to the up. Okay, it is also contains the metrics for the of the classification also, so it will be difficult to find it. So I can tell you that um, there is also other metrics like silhouette in like suppose say adjusted mutual information, which is the AMI, which is another external measure. There is another which is the NMI, normalized mutual information. There is another measure which is say silhouette coefficient, silhouette
Silhouette.
index. Yeah,
The basic jacket index is also there.
yeah. Jacket index is also there, but we have to check it whether it is provided or not. I'm not sure that Jacquard index is provided or not. All from learn fix code. Okay, it is provided. We can find Jacquard index also. So just call Jacquard score. It is also external measure.
Yeah.
What it is saying. Okay, we have to give this parameter. Okay, let's say macro is best currently. So average equals to macro. So by this we got this Jacquard score also. I have also code of Jacquard index, which I made by myself. I will add this to this. So
Okay.
yeah, and you can also use these measures also. Same.
Normalization.
Yeah. Are there any other doubts?
No, no, thank you.
Okay. So I'm stop
What?
sharing this. Okay.
Thank you, Mr. Atif, for this